Alright, tonight we're going to go over Chapter 6, which is all about static routing. Now, if you take in CIS 151, we did touch on static versus dynamic routing a little bit. So really, all you really need to know about static versus dynamic is with static, you're manually entering the routes, and with dynamic, the routes are learning themselves through different protocols, and the network kind of builds itself by learning about the different devices. So in a nutshell, that's basically the entire chapter, but we're going to talk a little bit more about the differences between the two, how the dynamic routes are actually created, and then how to actually create the manual routes on the hardware itself. So again, with static routing, we're manually entering in all of these addresses and paths. So it works for small networks, but if you're going to be getting into larger networks, you're going to want those to be dynamic, just because every time you make a change to the network, you have to go back into every single router and update those paths. So static routing, there's obviously some advantages over the dynamic, otherwise we just always use dynamic. With the static routing, the routes are not advertised over the network, so they're a little more secure. Static routes use less bandwidth than dynamic routing protocols, and it doesn't use any CPU cycles. And the CPU cycles for dynamic routing are used to calculate the fastest path to get to the next hop. And then again, with static routing, the path is static, and it only uses the route to send the data that it knows. The disadvantage is, however, the initial configuration and maintenance is very time consuming. You have to touch every single router and enter in those configs manually. It's very error prone just because, again, you're doing it manually and people make mistakes. You have to intervene anytime a route needs to be changed, and it does not scale well because growing networks, the maintenance becomes cumbersome. Again, you have to touch every single router to update that routing table. And then it requires a complete knowledge of the whole network for proper implementation. So you'd have to have the proper documentation that we talked about in Cisco 1. Make sure that you have your whole network documented and that you are not missing any routers and everything gets configured the same way. So there's three primary uses for static routing, providing the ease of routing table maintenance in smaller networks that are not expected to grow significantly. So again, in this first bullet, we want to stress small networks and not expected to grow. Change back to my arrow. I'll do laser pointer. That sounds fun. Okay. The other use, the routing to and from stub networks. Again, a stub network is, there we go. Again, a stub network is a router that's connected to a switch, so it's connected to some PCs, and the router is connected out to the internet or to the larger network. So there's only one router in this stub. Again, stub network is a network accessed by a single route, and the router has no other neighbors. So there's no other neighbors on this little stub network. And then the last use is using a single default route to represent a path to any network that does not have a more specific match within the routing table. So if it gets a address in, it doesn't match anything specifically in the table, it goes to the default route. Static routes are used to connect to a specific network, provide a gateway of last resort for a stub network, so that's that interface out to the rest of the world, and reduce the number of routes advertised by summarizing several contiguous networks as one static route. And then you can also use these to create a backup route in case the primary link fails. So for example here, if we had 192.168. 0, 192.168.1, 192.168.2, 192.168.3, 4, 5, etc. You could summarize that whole network as 192.168.0/16. So again, just a picture of a stub network. We have this little stub right here, one router, one gateway out to the rest of the world. So if I want to go anywhere in the world, target router 2, because that's what's connected out to the internet. Router 2 will know about the network, router 2 will know about the 2 network and anything in the cloud. So it knows about this one here and this here, but it doesn't know about network 3 because it's not directly connected. Router 2 would have to have a static route configured to go to router 1 to get to this 3 network. The default static route is a route that matches all packets. So again, if it doesn't match anything more specifically in the routing table, it goes to the default route. The default route identifies the gateway IP address to which the router sends all IP packets that it does not, or that it has not learned or have another static route for. A static route is simply a static route within quad 0/0. So 0000/0. That's the destination IPv4 address. Another example here of the summarized routes. So we have 172.20, 21, 22, 23. This would actually be a summarized route of 172.20.0.0/14. And I'll show you how to get that in a few more slides. Next, we have floating static routes. So with floating static routes, you can actually have 2 routes going to the same place. And then the floating route would only be used when the primary route is not available. So to do that, you will have to do a little bit of configuration. So by default, if you have 2 static routes going to the same destination and their cost metric is the same, or their administration distance is the same, it'll actually load balance the traffic between the 2 interfaces. So it'll send one out interface 0, it'll send one out interface 1, and then it'll just keep going and basically use that as one big link. But that kind of defeats the purpose of what we're trying to do with the backup route. So to designate the primary, you'd set leave the administrative distance alone on the primary connection, which is the private WAN in this example. And then the backup connection, we would actually put in a higher administrative distance value in that route. And again, I'll show you that in a command later. But for example, we would leave this one as 80 value of 1 or 0. Actually, it would be 1, not 0. 0 means something else. I'll show you that in a minute. But and then this one we would set it as 2, so that it's always going to go out 1 because 1 is less than 2. If for whatever reason, say this is Comcast, somebody cut a fiber line, no longer available. This is going through, say, CenturyLink. If the value of 1 is no longer available, 2 is the next lowest, and it'll start routing all your traffic out this way. And hopefully you don't notice any downtime on your side. So again, administrative distance is the distance that the router ranks the route. So if it's 0, it basically has no cost associated with it. It's a directly connected route. If it's a 1, it's a statically assigned route. 5, it's a summary route. And then we've got all these others here. I'm not going to read them all off to you. But the main thing you want to take away from it, the lower the AD, that means the route is more trustworthy. So 0, obviously it's very trustworthy because it's directly connected. 1, more trustworthy because I've told it that's where it needs to go. So how do we actually do this on the devices? To do this in global config mode, we're going to type in the command IP route, shown here. And then Cisco's syntax is a little bit difficult to understand. So in reality, I mean, your textbook is going to say this, what's shown on the screen here, but the way to think of it as this is your destination network and your destination subnet. So we do IP route, the IP address of your destination network, the destination MAC address, and then the interface IP address and exit interface. Sorry, this is the next hop interface, not the exit interface. So it'd be next hop IP address and then the exit interface. We'll show a picture here in a minute. So the next hop can be identified by an IP address, exit interface, or both. How the destination is specified creates one of the three following types. So the next hop route, only the next hop IP address is specified. It doesn't specify the interface to go out on, just knows the IP address to go out on. We can have directly connected static route, only the router exit interface is specified. So not necessarily the next hop, just the exit interface. And then we can have fully specified, which does both. It has the next hop IP address and the exit interface both specified. So if you go back to this command here, that would be all the information filled in. So looking at this a little further, in this example here, we have router 1 needs to send a packet to the 192.168.2 network. It's on the 192.168.3 network, so we need to send it through. So what the router is going to do is look up in its table. It's going to do something called a recursive lookup, something I want to remember, because this is on the final exam and it is on your certification exam if you go on to that. So router 1's going to say, okay, I need to send this out to, or I need to get to 192.168.2.2. Oh, cool, I have a static route for that. So I have 192.168.2, it's a /24 network, and I'm connected via 172.16.2.2. Cool, I know where to go. Wait a minute, how am I connected to this? So it does that recursive lookup. It knows that it needs to get here, and it knows it can get there through this address, but it doesn't know what interface to go out on. So it does a recursive lookup through its table, and it sees, oh, I can get to the 2 network by a directly connected route on serial 000. So it knows now I'm going to send this out serial 000. Another example here, the one thing we want to take away from this is if router 1 wants to target this 2 network, the next hop is always going to be router 2. It's never going to go directly to router 3, in this example at least, because router 2 is the next directly connected network. So to configure a fully specified static route, both the output interface and the next hop IP address have to be specified. This is another type of static route that's used in older iOSs prior to Ceph. What Ceph is Cisco Express Forwarding. And what that does is it builds a forwarding information base along with your routing table and neighborhood adjacencies. So it's actually looking at all these different values and then creating that path for you. So when that comes into play is if you had a situation like this down here, where you have a bunch of routers connected to a switch, well, router 1 needs to send information out here, but it's going to send it to a switch, so the switch could send it out to both interfaces, it could send it to all interfaces if it's never talked before. So using Ceph, it actually learns the interfaces that these other routers are on, and it just sends it out to the proper router. So just another example of this, we have router 1 connected to router 2, and then go into router 3, and we see all of these routes statically assigned here in the switch, or sorry, in the router. So how do we verify a static route on the router? So in the router, you can either use a ping or a trace route. That'll actually show you the whole connectivity of it. But if we want to see if the router is actually configured properly, we can use show IP route. We can use show IP route static, which will only show your static assigned routes. And you can also do show IP route and network, which will show you any networks attached to the network that you've specified. So if you did 192.168.0.0, it would show you anything in that range. To configure a default static route, we would use the same IP route command. So we do IP route. The destination is quad zeros. And then we do another set of quad zeros for the subnet mask. And then again, the IP address of the next hop, and then the exit interface. And again, all the static route is saying, if there's no better match in the routing table, use the default route. So in this example, again, we have router 1. We're going to set the default route to 000000, IP or subnet mask of quad zeros, and then IP address 172.16.2.2, which is actually going out serial 000. So it just says, I need to get out to the outside world. My default route tells me to go out to the outside world, send it out to the 2 network. Then in the router itself, we can verify that. We do the show IP route static, look for anything that has an S, and then the default. So here we have static, default is quad zeros /0, and connected via 172.16.2.2. IPv6 route, pretty much the same as the IPv4, except we have to add the 6, but the syntax is pretty much the same. So the command is IPv6 route, the IPv6 prefix and mask for the destination, and then the IPv6 address for the next hop, and then the exit interface. So with IPv6, the next hop can be identified by an IPv6 address, the exit interface, or both. How the destination is specified creates a few different types of routes. So next hop IPv6, only the next hop is specified. These are pretty much the same as the IPv4, but again, with the 6 in it. Directly connected static IPv6 route, only the router exit interface is specified. And then the fully specified, again, both the IP address of the next hop and the exit interface are specified. So we see that again in this picture here, where we have the route set to go out to this link here. So to target the next hop, we typically want to use the link local address of the interface. That's shorter. So for router 1, the link locals on this example is FE80:1. For router 2, it's FE80:2. And then we, in the configuration here, we see the command IP route, the IPv6 address, and then the next hop, which would be FE80:2. And then for the fully specified, we have the IP route, the destination, and the interface. Again, for the destination, we don't need the subnet mask, we just need the prefix length. And then we have the exit interface, and then the next hop. So same with IPv4, we can use commands to verify ping and trace out still work with IPv6. And then the show commands are show IPv6 route, show IPv6 route static, and show IPv6 route network. Again, they do the same thing as the IPv4, just outputs the IPv6 information. Default static IPv6 actually wins out as far as easier to remember or easier to type than IPv4. So for once, IPv6 is easier than IPv4. So with the IPv6 default route, we just do IPv6 route :/0. And again, you have to remember that :" specifies that there's 32 zeros, and that's a 48-bit number. Or sorry, 128-bit number. Then we have the IPv6 address, which would be the link local, and then the exit interface if you want to do fully specified. And then an example of a configuration here. We have IPv6 route :0 default route, and then this one doesn't do link local, it does the actual full, which is fine. No, actually it does do link local, but okay, same difference. And then verifying again, we can see that in the routing table we have a static route set to :0 and then via this IP address. So the last few slides we're going to talk about route summarization. So route summarization is also known as route aggregation, and it's a process of advertising a contiguous set of IP addresses as a single address with a less specific and shorter subnet mask. This is done with CIDR notation. It's a form of route summarization, and it's synonymous with the term supernetting. And what CIDR again stands for is classless interdomain routing, and the key point we're going to focus on is the C, or the classless. So again, CIDR ignores the limitation of classful boundaries and allows a summarization within masks that are smaller than that of a default classful mask. So if we're thinking of a 10 network, it doesn't necessarily have to be a /8. We can actually break those pre-classified boundaries and create our own. So this type of summarization helps reduce the number of entries in the routing updates and lowers the number of entries in the local routing tables. So to calculate the summary route, it's not that bad. What you have to do first is get the list of networks that you want to summarize and then convert them all out to binary. So in the slide it's already done for you. So 172 right here is in binary, and then 20 is right here in binary. We're not going to worry about these zeros over here because we don't have to. So what you're going to look at is where are they last the same? So where are they going to start to change? And we see that they're all 172 in the first octet, so it's not there. So we look at the second octet. They're all zeros, they're all zeros, they're all zeros again. Then they're all ones, then they're all zeros, then they're all ones again. So far, everything's the same. Where they start to differ is the last couple bits in the second octet. So again, we're going to look at where they differ. So we're just going to look at these first section, the first full octet, and then the first 6 of the second octet. So if we count all those up, there should be 14. So there's 8 and 6. And then we should, and then since we have 14 bits, it's a /14. So if we calculate that out, the subnet mask should be 255.255.252.0.0. And then that would be the subnet mask of your summarized network. So we do the first network in the range was 172.20.0.0. So we want to summarize that whole network. And the summarization would be 172.20.0.0/14. And then that will encompass the 21, the 22, the 23 network. So an example here shown in the routes, we have a summarized route, again, a little different than the one we did in the last slide. In this example, the first 22 bits are the same, so it'd be a /22 network, which would be 255.255.252, and the summarized route is 172.16.0.0. So it's actually going to only use this entry here, and that these 3 routes would be summarized into this one entry. So we can do the same with IPv6 addressing. So aside the fact that IPv6 are 128 bits long and written in hexadecimal, summarizing the IPv6 is actually very similar to IPv4. It just takes a few extra steps. So multiple static IPv6 routes can be summarized into a single static route, again, if the destination networks are contiguous, and can be summarized into a single network address. And then multiple static routes all use the same exit interface or the next IPv6 address. So to calculate the IPv6 network address, there are a few different steps. So we're going to list the addresses and the prefixes to identify the part that's different. So just like with IPv4, we're looking at where they start to change. Again, with IPv6, we can abbreviate them, so we want to make sure that you write it out in the expanded form. That way you don't miss any zeros or anything. Once you've identified the section that differs, convert that section from hexadecimal to binary to really pinpoint where it's changing. And then count the number from far left to the matching bits to determine the prefix length of the summarization route, or the summary route. Copy the matching bits and then add 0 bits to determine the summarized network address, or the prefix. Once you're done with that, convert the binary section back to hexadecimal, and then append the prefix of the summary route. So what you got in step 4 is what the new prefix will be. So with floating static routes, with IPv6, we can do the same thing that we did with IPv4, where we add the administrative distance. Actually, I think this slide's a little bit out of order because the next slide is showing me IPv4 again. But whatever, we can recap on it. So to recap floating static routes, the administrative distance of the static route can be increased or decreased to make the route more or less desirable than another static route. In this way, the static route floats and it's not used when the route with a better AD is active. So this is that redundant link that we talked about earlier. So again, just shown here, this router has 2 links. Yeah, these slides are definitely out of order. Okay, good to know for future, but we can deal with it for tonight. So again, this router has 2 static routes. Route 1 goes to router 2, route 2 goes to router 3, and we always want the traffic to go out of interface 00 unless this link goes down. Then we want it to go over to 01. So to do that, we do IP route, set the default, and then set the exit network, and then leave the AD as blank, which is defaulted to 1. And then for the link to go out serial 1, we're going to set IP route, and then the default route, and then we're going to set it to the 10 network, which goes across here. And then we're going to manually set that AD to 5. That way the AD distance is higher, and it'll always go out 000 unless 000 can't route traffic, then it goes out 01. The last slide, to test the floating static route, we can use a few different commands. We can use a show IP route command to verify that the table is using the default static route. We can use a trace route command to follow the traffic flow of the primary route. So again, if you do the trace route command, it sends a series of pings and it'll actually output on your screen what all the hops taken were. So it'll actually show you every router that the packet goes through. If you want to test the redundancy, you can actually disconnect the primary link or go into the router and do a shutdown command on the exit interface and then make sure it fails over. You can use a show IP route command to verify the routing table uses the floating static route. And then use a trace route command again to follow the backup route to make sure that it's going the right way. And that is it for chapter 6. So we are just a little over halfway through the semester. If you guys have any questions, always feel free to reach out to me. I'll get back to you as soon as I can. But that's all for tonight, and have a good rest of the week.